to gravitational waves. So take it away, Lukas.
Yeah, many thanks. Yeah, thanks for the invitation. I'm very happy to speak. And I'll be reporting about work done with my colleagues Jacopo Fumagalli and Sébastien Reynaud-Petel at the Institute of Astrophysics in Paris. And what I will tell you about has appeared in a paper in December, but also I'll be reporting about work in progress. And the plan for this talk is to basically start and tell you about lots of phenomenology and cosmology, but then in the end arrive at implications for string theory. So this talk is about inflation, which is a phase of accelerated expansion at the very beginning of the universe that sets the initial conditions for the subsequent hot Big Bang era. Inflation has become one of the standard paradigms for understanding the early universe, but at the same time, it's fair to say that we do not have a fundamental theory of inflation. And the work I want to report about is one part in this greater narrative and quest towards finding out about the mechanism that is behind inflation. Having said that, while we do not have a fundamental theory of inflation, still it's not difficult to model inflation theoretically. And the standard paradigm for this is in terms of a single scalar field with a positive potential coupled to gravity, and that field, the inflaton, slowly rolls down this potential. This picture of single field slow roll inflation has very precise predictions for the primordial scalar fluctuations. Firstly, they're nearly scale invariant. They give a nearly scale invariant power spectrum. And furthermore, they obey pretty much Gaussian statistics. What is very nice is that this simple picture already agrees with experimental data that we have from the cosmic microwave background and from large-scale structure surveys that confirm the scale invariance and nearly Gaussian statistics. So let me show you such a nearly scale invariant power spectrum plotted here against time during inflation in units of e-folds, or equivalently in terms of some inverse length scale k. And scale invariance simply implies that the power spectrum is more or less constant throughout inflation. And here it's also set to the amplitude 10 to the minus 9 that's implied by cosmic microwave background observations. What I want to highlight, though, and what is important for the work I want to show, is that this experimental data is only available at large scales greater than roughly 1 megaparsec. So what this implies is that observations of the microwave background and large-scale structure only constrain inflation over some order 10 e-folds, some 60 e-folds before the end of inflation. And even though these constraints are very strict during this early phase of inflation, in fact, the later stages of inflation are not really constrained by this. And furthermore, there are very little other constraints at these small scales, and hence the power spectrum that I've shown you with this nearly scale invariance, also continuing towards the later stages of inflation, is in fact an extrapolation from this early phase. At these small scales, we really, experimentally, it's permitted to have departures from scale invariance, that is to have deviations from single field slow roll. And here in this talk, I will talk about one particular type of deviations, something that's very interesting from the observational point of view. What I want to talk about are sharp transitions during inflation. So imagine having a phase of something like single field slow roll. However, then there is some sharp transition before single field slow roll behavior picks up again. Sharp in this context means something very precise. In fact, that the transition occurs in something like less than 1 e-fold of expansion. And to give you some pictures, explicit realizations of such a sharp transition are, for example, a short period of violation of slow roll, for example, due to a sharp step in the inflaton potential. Or if you want to go beyond single field in a multi-field setting, such an effect can also be observed if you have a very sharp turn in the inflationary trajectory. What is common to all these microscopic realizations of such a sharp transition is that the scalar power spectrum follows the following template. It can be written in terms of a sinusoidal modulation of an otherwise smooth envelope. In particular, it is the signature of this sharp transition to find k-periodic sinusoidal modulations in the power spectrum. And in particular, the frequency is also determined precisely. It's set by the scale that exits the horizon exactly at the time of this sharp feature. In addition to the modulation, I want to emphasize another effect. If this particular transition is sufficiently strong in some sense, so for example, for the step in the potential, this means that you accelerate quite a lot. You reach a large speed compared to the speed during slow roll, or for the turn, if this dimensional rate of turn is particularly large, then the amplitude of fluctuations is also enhanced, and this envelope of the scalar power spectrum exhibits a peak. So what this looks like in the scalar power spectrum, if you have such a sharp feature at small scales, you find that the power spectrum exhibits a peak, and in particular, this peak is actually modulated by oscillations. Now, this is particularly interesting from the observational point of view, since this can be tested. In particular, if scalar fluctuations are enhanced significantly compared to CMB scales, then fluctuations can lead to overdensities that eventually collapse to primordial black holes that can then be a significant part of dark matter of the current universe. Furthermore, these scalar fluctuations, they also induce gravitational waves. And again, if the amplitude is sufficiently enhanced, the resulting gravitational waves may be visible in the upcoming generation of gravitational wave observatories. What is particularly interesting regarding these sharp features is that these oscillations in the power spectrum, they also induce a characteristic signal in the stochastic gravitational wave background. And that's the main subject of the work that I want to tell you about today. This implies that by finding these oscillations, observing such an oscillation in the background, one can very easily learn about inflation and the early universe. So just for the rest of the talk, I want to tell you more about these scalar-induced gravitational waves due to such a sharp feature. But then I want to return to string theory and mention a couple of implications. Scalar fluctuations induce gravitational waves at second order. And this results in the following. Regarding these primordial fluctuations from inflation, one finds that they then produce gravitational waves with an energy density in units of the critical density per log periodic frequency interval that is given by the following expression. In particular, this energy density fraction can be written as a double integration with some integration kernel over the square of the scalar power spectrum. This is a non-linear relation between the scalar power spectrum and the gravitational wave spectrum, making it not very easy to analyze analytically. And furthermore, there are a couple of caveats to report here. What I've written down here is in fact only the contribution to gravitational waves from inflationary fluctuations sourced after inflation, when these fluctuations re-enter the horizon. There is also a second contribution induced during inflation, which is often slow roll suppressed. So while for a complete result, the second contribution should also be taken into account, there are also many models where what I've written here is the dominant contribution to the gravitational wave spectrum. And there are a couple of further assumptions. This gravitational wave spectrum depends somewhat on the thermal history of the universe. And here I've assumed that after inflation, we experience a period of radiation domination, which is the canonical picture in cosmology. Now, given this expression for the gravitational wave spectrum, the question is how the oscillations in the scalar power spectrum that we observe for a sharp feature are processed and manifest themselves in the gravitational wave spectrum. To give you some ideas about this, let me first talk about a scalar power spectrum that exhibits a single narrow peak. For a single narrow peak, this has been analyzed in the past, and one finds that the gravitational wave spectrum takes the following characteristic form. You find some broad lower peak at lower frequencies, and then a principal higher and sharper peak, which comes from resonant amplification. And furthermore, the location of the peak, of this resonance peak in the gravitational wave spectrum is directly related to the position of the peak in the scalar power spectrum. This insight can be used to learn about the gravitational wave spectrum due to an oscillation. In particular, we use this as one of our strategies to analyze this gravitational wave spectrum. And the idea is to simply take a power spectrum of an oscillation and simply model the individual oscillations as a series of peaks. The gravitational wave spectrum due to a series of peaks has also been studied before independently, and one can find the following results. First of all, every individual peak itself gives a contribution to omega gravitational waves that has this characteristic form for a peak, in particular with a resonance peak. And furthermore, due to a series of peaks, the situation is a bit more complicated, given that omega gravitational waves depends on the squares of the scalar power spectrum. There can also be instances where two different peaks in the scalar power spectrum interact when they get integrated over one another in this convolution-like integral. And you also find further resonances in the gravitational wave spectrum due to this interaction of individual peaks. Overall, you find that you can predict the location of maxima in the gravitational wave spectrum like this. And there is also a constraint which comes from the fact that this integration range in this integral is restricted, and not all peaks can interact with one another. But from this, you find a gravitational wave spectrum that is a superposition of all these different contributions. And in the end, what you find is that from the superposition, there is still an oscillation left. And you can also predict the period simply by analyzing the separation of resonance peaks. And one finds that an oscillation in the scalar power spectrum leads to a similar k-periodic oscillation, but with a higher frequency. To show you just an explicit example, let me not show you some toy model, but turn to an explicit model. And this is the example model that we used in our paper, which is the realization of a sharp feature in terms of a sharp turn in the inflationary trajectory in multi-field inflation. So you take a multi-field Lagrangian, but for the minimal setup, you can work with a two-field model, and the relevant parameters to describe this model are delta, the duration of the turn in units of e-folds. There is eta perpendicular, the dimensionless rates of turning, and there is also the scale of the feature introduced before. And for a simple turn profile, you can then in fact calculate the scalar power spectrum in this model explicitly, and this is the result. I just want to show it because it can be done, and I want to show it to really exhibit that this really does take the form of a sharp feature. You can identify all the different ingredients of this template. You find the sinusoidal modulation with the frequency given by a 2/k feature, and one also finds an envelope, in fact, also with an exponentially enhanced peak. So for this example, let me show you two models and display the scalar power spectrum and the corresponding gravitational wave spectrum. So here I've chosen two models where I choose parameters so that they share a common envelope. However, they have different frequencies. So in model 2 has a frequency that's twice that of model 1. And here we have the gravitational wave spectra. And the first observation is the two models that share a common envelope, overall they have a gravitational wave spectrum whose overall shape is the same. So the overall shape is really effectively determined by the envelope. And we also see oscillations as predicted by our resonance peak analysis. In the right plots, they're not very well visible. So let me turn to a different plot where I take the gravitational wave spectrum over the range of this peak and simply compute the ratio of the full result with the smoothed version given by the black dashed line. And that's what is shown here. And basically one finds that the oscillation in the gravitational wave spectrum is also sinusoidal. And we make another important observation. In the scalar power spectrum, the oscillations had the same amplitude. It was order 1, it was amplitude 1. However, in the gravitational wave spectrum, the example with the higher frequency has oscillations with a smaller amplitude. So a higher frequency, more wiggles lead to some averaging out effect, leading to a smaller amplitude. Overall, we find that even though the amplitude was 1 in the scalar power spectrum and gravitational waves, it's of the order of 10%. So this is the result which may not have been expected naively due to this non-linear nature of how scalar fluctuations are processed into gravitational waves. But here we are, and this is the summary for a sharp feature given a scalar power spectrum with following this template for a sharp feature. Near the peak, near the principal peak, the gravitational wave spectrum can be written as follows. It can again be written as some sinusoidal modulation of some otherwise smooth envelope. We can also make a very precise statement about the frequencies that are related with this factor of square root of 3. What's less straightforward to say in a model independent way is how this envelope behaves, since this envelope of the scalar power spectrum determines the envelope of gravitational waves. But this is a much more model dependent statement. And we also find some interesting relation between the amplitudes, where in general there is some averaging out effect, so that the amplitude in the gravitational wave spectrum is typically smaller and at best can reach 10%. But this is an interesting result, since in principle, a modulation is something that can be seen experimentally and can be extracted from experimental data. And it's also a very characteristic signal which can then be directly related to properties of the scalar power spectrum, and from this to properties of the inflation model behind it. So for the example of a model with a sharp turn, here we also show various implementations of a sharp turn that occur during different stages during the later stage of inflation. For example, some 15 e-folds after CMB modes, 28 e-folds after CMB modes, to show that basically all the range of future gravitational wave observatories can in principle be helpful in searching for these sharp features. So far, I've mainly talked about sharp features, but I also want to mention one more aspect. At small scales, we can also have a different effect. There are also models where we find a so-called resonant feature. This is caused not by a sharp transition during inflation, but if you have some oscillation in the background evolution of inflation. So this can occur, for example, in monodromy inflation, or for example, when the inflaton is injected in some valley and then oscillates about the minimum of that valley before settling. In this case, the scalar power spectrum again has a modulation. However, this time it's periodic in log k, in not k. Again, this can be analyzed regarding the induced gravitational waves. And here, the findings are qualitatively similar, but with some important differences compared to the sharp feature. Again, we find modulations in the gravitational wave spectrum, but the resonant case is a bit more intricate, where we find a superposition of two different oscillatory contributions, one with the original frequency of the scalar power spectrum and one with twice the original frequency. Now let me turn quickly to some implications for string theory and string phenomenology. Before doing so, let me also make a general remark. When studying inflation in string theory, many models that have been considered in the past, they aim at reproducing single field slow roll for 50 to 60 e-folds. One message of my talk that I want to get across is that from the observational point of view, this is not strictly required. We can have deviations from single field slow roll at small scales at later stages of inflation. Inflation can occur in different bursts of some order 10 e-folds, and which seems to be something that may be more amenable, in fact, to the picture of string theory and string compactifications with all its complexities of multiple fields and complicated potentials. So I want to advertise to embrace the complexities of inflation in string theory, as this is something that is not in conflict with data as such. However, also embracing the complexities of string compactifications and going beyond single field slow roll is technically difficult. Analyzing flux potentials for more than 2 complex moduli becomes very, very hard analytically very, very quickly. But now, should we really speak confidently about inflation in string theory, given the status of the field? In particular, I think about open questions regarding theoretical control of KKLT, including the uplift, and the overall attainability of de Sitter or inflation quasi de Sitter in string theory. Despite this objection, or to counteract it, I want to turn a little bit to recent history. And I want to emphasize that, in fact, there have been questions in inflation that have been powerful drivers for theoretical developments in string compactifications. For example, the question of the possibility of large field inflation in string theory was crucial at the beginning, when we started developing and sharpening swampland conjectures, such as the weak gravity conjecture and the swampland distance conjecture. And so by thinking about large field inflation in string theory, we managed to learn both about inflation, I think, but also about string compactifications. So I would advertise continuing to do so. And there are a couple of very explicit questions that arise in string compactification regarding the possibility of these sharp features that I've been talking about. To give a couple of examples, let me just mention 3 questions where I think string theory can give some answer, or it would be nice to get the stringy input. For example, sharp features require, one way of obtaining a sharp feature is to realize a sharp step in the potential. An obvious question then is it possible in string theory to create such a sharp step? Well, it may sound a bit trivial, but here, I mean, really, it needs to be a step that links 2 very flat plateaus, which are both suitable for inflation. And I can think of analyzing such a question, for example, in a setting with an axion with several instanton contributions to the potential. And I can imagine that there are constraints coming from weak gravity, conjecture considerations, and so on. Another question that's interesting for sharp features is whether there are bounds on the field space curvature. And this arises as follows. In the model of a sharp feature in terms of a sharp turn, to get a significant amplification of scalar fluctuations, one needs to turn by a large angle. And in fact, to reach, for example, an amplification of 10 to the 7, which is important to create primordial black hole dark matter, one would need to turn by 4 pi, which is impossible to do in a flat field space. This would require a curved field space, which is only too natural in string compactifications where generically moduli spaces are curved. This will also be true for the reduced moduli spaces in inflation models. But an interesting question would be, are there some sort of bounds on the field space curvature, which would in fact then also bound the maximal amplification in such sharp feature models? And finally, the model with sharp turns also leads to the following question. If I consider several sharp turns in a row, I can imagine a situation where I work in a moduli space that satisfies the refined swampland distance conjecture, where along a geodesic, I I find a tower of states that becomes exponentially light after roughly 1 Planck unit in distance in field space. However, by following a trajectory with multiple turns, I can prolong this beyond into the trans-Planckian regime, which would be in violation of this refined swampland distance conjecture. So another obvious question is, would there be a bound on this rate of turn that I can do in a given field space? So this is basically the summary. My main point is departures from single field slow roll are interesting, in particular sharp features, sharp departures, as they lead to a characteristic signal in the gravitational wave, stochastic gravitational wave background that can potentially be observed with future experiments. And I expect string theory to place bounds on these inflation models with sharp features, and I'll be very happy to know the result of this. This will, however, require addressing the difficult questions of how really the potential in string compactifications is constrained. But I want to argue that this is, I think, an effort that is certainly worthwhile. So yeah, many thanks for your attention.
Great. Thanks, Lukas, for your very nice talk. I'll wait for questions in the chat. I have 2. So the square root of 3 that appeared like so often, why is there an understanding of why the frequency gets bumped up?
This is really directly related to assuming that it's that all these relevant fluctuations re-enter the horizon during radiation domination, and it's the 3 that is floating around always in radiation domination.
Well, makes sense. And you talked a little bit about detecting this gravitational wave signature in upcoming experiments. Is there a feature that I can rely upon to distinguish this source of gravitational waves from other ones? I mean, could I possibly resolve this oscillatory behavior?
Of course, the characteristic thing would be the oscillation. Then maybe one can find other mechanisms that produce oscillation, but here it's a very distinctive feature. Yeah, the question is, can one see these oscillations? One can do some preliminary studies whether there is enough frequency resolution to find these oscillations, and this seems to be the case. The main question is whether the amplitude is enough, since they're at most 10% of the signal, and for this, some more dedicated analyses would need to be done, and we're looking into this.
Okay, cool. And Irena, this question.
Yeah, thank you, Lukas. Nice to see you. So I have a question. When you mention a possible bound on the curvature so that we can turn the trajectory a lot. Exactly, like for when we have a Keller potential which is minus log of something, in the simple case, the curvature is constant and depends on the integer in front, like the 2 that you put here.
Absolutely.
Do you have an intuition of how big this integer should be so that you get this curve, this turning? I mean, that you get the enough scalar fluctuations. I mean, like if I tell you that cannot be bigger than 3, is that already enough, or like how?
Yeah.
How big should it be?
No, I can't give you a precise number. However, even the question is, should it be positive or negative? And of course, if we start out, then we start with negative curvatures. But inflation models typically restrict to some sub-moduli space. So some of the moduli here will be stabilized and become constant. So overall, the effective curvature for this leftover modulus in the pseudo-moduli space that's then left, I think, can be quite different. Yeah, the question would be to find what do we need phenomenologically? Do we need to maybe even to be positive and large to?
Yeah, that's my question. Like, for example, imagine that I tell you, for simplicity, it's a constant curvature. What do you need phenomenologically? Do you need it to be positive, negative? How big? Like, is there any bound on this that is already known, or? No, not yet. Okay.
No, yeah.
Okay. Thanks.
And for a final question, Jakob?
Hi, Lukas. Nice to see you.
Hey.
Thanks for the talk. just as a follow-up to what Irene asked, is it actually necessary to have field space curvature? You could also think about axion monogamy, where you just basically wind up a logarithm over many sheets. Wouldn't that work too?
Exactly. I think, or you could try then to go to equivalently even to a higher dimensional model. This is specifically now for a 2D model, where again, realize this winding in actual field space. But there again, then you need trajectories that are maybe close by again, and you need to have a potential that really keeps you on these individual repetitions, copies. So I think that the 2D setting would be a good starting point to get some ideas, since some of these things tend to generalize to the more complicated settings. Yeah. But yeah, absolutely.
Okay, thanks.
Cool. So with that, perhaps we should thank Lukas with our clap emoji.